My name is Nadav Iran, and I'm the VP of Engineering for Google's ML infrastructure products. Our mission is to drive ML excellence for Google and the world. We create the tools, frameworks, languages, and services to power Google's AI-first strategy, and we make them accessible to all of you, so you can build the things that you care about. So let's start with what we've been working on with machine learning at Google. ML powers amazing things, from night sight in pixel to reconstructing thousands of particles in one go at the CERN Large Hadron Collider with TensorFlow. While it may feel like magic at times, it's simply advanced technology, made possible by tools that are easy to learn and use to solve your own problems. The goal of any platform is to let you build solutions to your problems, and we're working to build one for machine learning that can be used in your business, your hobby, or even cutting-edge research. When building ML solutions, you work with data, with ML models, with conversion to different runtimes, with optimization, deployment, MLOps, and a whole lot more. So let's take a look at some of the major parts of the ecosystem, like TensorFlow. We open source TensorFlow to accelerate machine learning research and empower developers around the world to build AI applications. That was 6 years ago today. And we're so happy to celebrate TensorFlow's birthday with you all. TensorFlow has expanded into a vast ecosystem of tools and frameworks that help you along your developer journey. Let's take a closer look at the ecosystem, starting with Applied ML. We'll start with the tools we have to go from data to production. From your first and simplest Hello World machine learning model, you can use the high-level APIs from Keras. The same skills will transfer to more cutting-edge problems. We often hear that machine learning models can be opaque, and we'd like to understand how, for example, a computer vision model determines what it sees. With research into class activation maps, there are techniques to see what the model pays attention to. So here you can see simple Keras code that shows us which part of the image the model paid attention to when it classified a cat. It was the cat's face. Because of how it can be used in problems, from the simple learning one to the more complex research-oriented ones, as I just showed, we believe that Keras is the best framework in the world for applied AI. And it's our primary high-level API for developers using TensorFlow. It's not just for getting started. Let's look at some of the new advancements. In TF 2.4, multi-worker mirrored strategy was released. Keras models now support training on TPUs, GPUs, multi-GPU machines, or clusters of multi-GPU machines by simply switching their distribution strategy between TPU strategy, mirror strategy, and multi-worker mirror strategy. In TF 2.4 as well, the Keras Mixed Precision API was released, allowing faster training on GPUs in float 16 mode, as well as bfloat 16 memory optimizations on TPU, with automatic loss scaling. In TensorFlow 2.6, Keras preprocessing layers were released, making it much easier to add preprocessing capabilities to your models. They had multiple preprocessing layers for categorical data, replacing the feature columns API from TensorFlow 1. Preprocessing layers also add a new comprehensive text vectorization layer that will make your NLP models much more readable. Additionally, as of TF 2.6, Keras has been modularized as a separate pip package on top of TensorFlow, installed by default when you install TensorFlow, and now lives in a separate GitHub repository at the link shown. This will make it much easier for the community to contribute to the development of Keras, and we welcome your PRs. And we know that as developers, efficient problem solving doesn't equate to building all your models from scratch. Discovering these models and how to use them isn't always easy. And with that in mind, we created TensorFlow Hub. On TensorFlow Hub, you can find hundreds of pre-trained models for video, image, text, speech, and audio. For example, here's a simple model we trained for comment spam detection. You can find it in Hub and then test it easily. Or this bird detection model where we can upload a picture and get it classified. And of course, when you want to use the model to solve your business problem, you don't have to do it by yourself. TF Hub will show you how to do it, which layers to freeze and which ones to use for activations, etc. We just saw a browser-based tester for models with the comment spam and image classification. And think about that. It was a model running in the browser, which means anyone, anywhere, can try your research with a click of a link. No dependencies to install or environment to set up, and usable by billions of people around the world. This is powered by Tensorflow Js, our JavaScript implementation of TensorFlow that enables you to run or train models anywhere JavaScript can run, which is pretty much everywhere. JavaScript can run in the web browser, on device, server-side, native applications on both mobile and desktop, and even IoT devices like a Raspberry Pi. As such, TensorFlow Js has seen enormous growth in the last few years. You're not limited to just running models in JavaScript. You can also train them too. And we've designed the APIs to be very similar to the Keras Layers API you saw earlier, so your knowledge in model architecture design and programming skills can be reused within the browser. We also make use of the GPU where appropriate to speed up training and inference in the browser. We see a lot of companies using TFJS in production. For example, Include Health use it to enable remote physiotherapy at scale while maintaining the user's privacy. Here, we see Movenet single-person detection model. We also just recently launched a new multi-person detection model of Movenet. This model can not only detect multiple people, but also track their movements. As shown here, even if two people exchange positions, the model can still identify whether the person who moved positions is the same person. For more inspiration, check out what the TensorFlow Js community has made by searching #MadeWithTFJS on social media. We've just seen deployment of models to the browser, but of course, there are many other places you can deploy them, such as to mobile devices. We're going to continue to see ML move from a niche market to being the building block of everything we do. And I believe Google is on the path to delivering the technology that will shape so many products and research in the future. With that, I'm going to turn it over to Kamal to discuss how we help you be ready for mobile, microcontrollers, and other edge devices.
Hi, my name is Kemal Al-Mujahid, and I'm a product director for machine learning at Google. While the number of edge devices continues to increase, they're also becoming more powerful, making it possible to build ML-powered apps that we would have never imagined before. And we want to put this power in your hands, no matter where you are in your developer journey. Whether you're an iOS or Android developer, we want to give you the tools to be successful. The first place to start with is MLKit. For common ML use cases, MLKit offers easy-to-use production-ready turnkey APIs. From barcode scanning to language identification, MLKit offers 13 unique cross-platform APIs which run well on both low-end and high-end devices and are completely free to use. We're continually adding new APIs and updating existing ones, so you can be assured that you will always have the latest and greatest that Google has to offer. For developers with more custom needs, we provide TensorFlow Lite, Google's open-source ML framework for on-device inference. TF Lite is used widely for powering on-device ML in Google Apps, as well as popular external apps on more than 4 billion devices. In addition to model inference, we recently launched on-device training in TF Lite. You can now train your TF Lite models on mobile and other edge devices, just as you would train your TensorFlow models on server. On TF Lite, we continue to work on making performance better. XNNPack, a library for faster floating point ops, is now turned on by default in TF Lite, allowing your models to run on an average 2.3x faster on the CPU. Once you've trained and optimized your model, the next step is to distribute it as widely as possible. To help with that, we're adding the TF Lite runtime to Google Play services, so you don't have to bundle it with your app. This means no additional APK size increase, plus you get automatic future updates. Many apps have already deployed this feature in production. If you're interested in trying it out, you can sign up for an early access program. Attend the on-device ML talk later to learn more. And finally, you can now run the same models in the browser thanks to TensorFlow Js. This means they'll work on feature phones as well as desktop Electron apps or anywhere else JavaScript can run. This lets you use the same model across billions of mobile devices running Android, iOS, Linux, and other edge devices. Let's take a look at an example of an app powered by TF Lite. Lookout on Android helps people get details about objects and text around them. This is especially important to help people who are blind or low vision complete daily tasks faster and more easily. Lookout recently introduced a new mode, Food Label. With Food Label, you can quickly identify packaged foods by pointing your phone's camera at the label. Lookout will guide you to position the food product so that it can be properly identified through its packaging or barcode, helping a user distinguish between, say, a can of corn and a can of green beans, which would both feel identical to the touch. Lookout's different modes, including its object classifier and OCR models, are powered by TF Lite. We also know that you need to run your models across vastly different hardware, from the latest and greatest phone all the way to tiny microcontrollers. There are now hundreds of billions of microcontrollers and embedded systems, and with TF Lite for microcontroller, you can run ML models on microcontrollers with only a few kilobytes of memory. So for now, we've talked about a simple workflow, from building to deploying a single model. But when we move to production ML, we discover that workflows are typically more complicated, and there is a lot more that is needed to be successful. At Google, we've measured the ML model code to be something like 5% of the total code necessary to train and deploy a model in production. All the other tools and infrastructure that you see here are critical. Now, how do you manage such a large operation? With machine learning operations, or MLOps. MLOps is an ML engineering culture and practice that aims at unifying ML system development, dev, and ML system operations, ops. Practicing ML ops means that you advocate for automation and monitoring at all steps of an ML system, including integration, testing, releasing, deployment, and infrastructure management. Like DevOps, we also need processes and infrastructure for continuous integration and continuous deployment. For that, we use TFX, an open source solution for the entire problem of machine learning operations, from storing and pre-processing data to model validation. Let's take a look at an example. OpenX operates the world's largest independent advertising exchange. At a basic level, the exchange is a marketplace connecting tens of thousands of top brands to consumers across the most visited websites and mobile apps. They used a TensorFlow serving deployment running on Google Kubernetes engine, serving 2.5 million prediction requests per second, under 15 milliseconds each. They've been able to make dozens of improvements to their model, everything from changing the architecture of the original model to changing the way certain features are processed without support from any other engineering team. Now, as always with Google tools, we're working hard to make AI fair and responsible. To that end, we've integrated the fairness indicators and the Model Card Toolkit directly into TFX. I'm also excited to announce V0.4 of our language interpretability tool, or LIT. LIT is an open source platform for visualization and understanding of NLP models. This new release includes new interpretability techniques like TCAV, Targeted Concept Activation Vector. TCAV is an interpretability method for ML models that shows the importance of high-level concepts, for example, color, gender, race, for a prediction class. Now say that you're looking for a managed system for MLOps. Vertex Ai is a new managed machine learning platform available through Google Cloud to help you with TFX at scale. Vertex Ai has tools that span the entire developer workflow, from data labeling, notebooks, and models within a single console experience, to prediction tools and continuous monitoring. All these offerings may be familiar to you, but what really distinguishes Vertex Ai is the introduction of new MLOps features. For example, Vertex Ai gives you the flexibility to use AutoML, which automates model training so you can build sophisticated models faster, using tabular text, image, or video data, as well as custom model training and explainable AI. And we've seen exciting user adoption. Since we announced general availability in May 2021, the volume of training has increased by over 70%. The volume of predictions has doubled. The number of GPU hours for prediction has doubled. And the total volume of API requests has tripled. Let's take a look at an example. Waze is the world's largest community-based traffic and navigation app. As part of its offering, it lets advertisers put their businesses on the Waze map. Waze approached improving ad delivery as a learning-to-rank ML problem. They ranked candidate ads to maximize the likelihood of ads to be displayed on the mobile client. They use Vertex AI suite to train and deploy a TF model and easily integrate with the rest of their data stack. Waze has seen great results, up to 19% lift in pins displayed per session in large markets. Vertex AI delivered low latency predictions within their performance parameters and helped smooth scaling of resources as ad traffic changed through the day thanks to CPU-based autoscaling. Data scientists at Waze noted that using TFX and Vertex AI for things like data validation, transform deployed to data flow, monitoring, etc., felt like magic. All these ML frameworks and tools originally came out of research, and we're making them accessible and easy to use for you. Because ML is such a fast-moving field, it's very important for us to keep helping researchers push the state of the art and keep flowing their innovation into our ecosystem. So I'm going to turn it over to Lawrence to share some of our newest research tools.
Hi, my name is Lawrence Moroney, and I lead AI and ML advocacy here at Google. Let's take a look at how the Google ML ecosystem tools are used to push state-of-the-art research. And we'll start with how we can do research at scale. The Google TPU is a piece of hardware that's managed in the cloud, and it deeply integrates with TensorFlow. It's designed from the ground up to accelerate machine learning and deep learning workloads for both training models and performing inference with them. With pods, TPUs reach their full potential, and when hundreds of these individual boards are connected together, they form AI supercomputers. To learn how TPUs ran novel edge-based graph convolutional neural network architectures to design later generations of TPUs, make sure you watch the chip floor planning with deep reinforcement learning talk a little later. For your research-friendly framework needs, we have T5X. T5X is a modular composable framework. It's used for high-performance, configurable self-service training, evaluation, and inference of sequence models. And here's an example using language at many different scales. The model has over 11 billion parameters, and it was trained off of the colossal clean-crawled corpus dataset. That's just one example of how our tools are being used in research, and we welcome you to try it for yourself through the TPU Research Cloud program. You can join the thousands of other researchers who've tried cloud TPUs for free. Our motivation is simple. We believe there should be no blockers in talent being equally distributed throughout the world, and we want to make sure that everyone has the opportunity to access state-of-the-art hardware and software for researching cutting-edge AI. And there's so much going on in cutting-edge research right now, but I'd like to highlight one project that I find particularly appealing. It's called PathDreamer, and its initial goal is in indoor navigation. Consider what happens when you walk into a dwelling that you haven't previously been in. From visual cues around your environment, you can likely infer which rooms might be the kitchen or the dining room or a bathroom. But how would you train an autonomous agent to recognize those same cues? Given just a single observation of an environment, PathDreamer synthesizes high-resolution, 360-degree observations up to 20 feet away from the original location, including around corners. And here we can see video that simulates reconstruction of the interior space of an apartment that was previously unseen. And the model infers what various rooms may look like, even though they were hidden around corners in the original picture. It's been built using TensorFlow and Keras, and it's fully open-sourced and available for you to explore today on GitHub. While Keras has a great high-level API, sometimes you need to go that little bit lower level. And with that in mind, we have JAX, a Python library designed for high-performance numerical computing. Here's a sample of JAX code, and you can see it's just ordinary Python plus NumPy. But what's really nice about this is that your code will execute on a variety of accelerators, so you can run your JAX code on a GPU or a TPU without further modification. And JAX libraries are compatible with TensorFlow. So for example, you can use TensorFlow data pipelines to input data into JAX. If you want to learn more, check out the talk JAX, Accelerating Machine Learning Research on this stream later today or on demand at youtube.com/TensorFlow. You probably have heard about the amazing work DeepMind did with research into protein folding that stands to transform biology. But did you know that they use TPUs and JAX to achieve this? So let's hear from Tim Green at DeepMind, who's going to tell us all about it.
Hi, I'm Tim. I'm a research engineer at DeepMind, and I'm going to tell you today about how we've used TensorFlow and JAX to solve one of the biggest scientific questions in biology: how proteins fold. Proteins are molecular machines essential to life. From our hair to our immune system, they're involved in every aspect of our bodies. Proteins are made of chains of amino acids, which fold into elaborate 3D shapes. The exact 3D shape that a protein makes is important for understanding what it does. And so knowing the 3D shape of a protein helps us to tackle diseases like COVID-19. You might have heard of the spike protein of the coronavirus, for example. Normally, the 3D shape of proteins can only be determined by laborious experiments and can take skilled researchers a long time to carry out. For 50 years, it's been a standing scientific grand challenge to predict protein structure from their amino acids sequence. AlphaFold changes this. How does AlphaFold work? AlphaFold uses deep learning to predict the 3D shape of proteins from their sequence of amino acids, almost like translating between languages. And as with many modern language models, it makes use of attention mechanisms along with a number of other neural network architecture innovations. If you want to know more, please read our blog post and paper. AlphaFold makes predictions to such a high level of accuracy that in most cases it matches experiments. How do we know this? So, CASP is a biennial blind assessment of protein structure prediction. The chart you are looking at shows the performance of the best entrant for CASP from 2006 to 2020. You can see the impressive progress in the last few years. After the 2020 assessment, the last line, AlphaFold was recognized as a general solution to the protein folding problem. Our research that led to the development of AlphaFold involved trying many different ideas. The Google ML ecosystem allowed us to iterate very quickly and then to scale up our research. AlphaFold is trained with 128 Tpu V4 cores over a couple of weeks. This is actually quite cheap compared to some modern models. TPUs are very fast, and training at pod scale allowed us to do things like running with a single example per core, which is necessary due to the high memory consumption. When it comes to using AlphaFold to predict a protein structure, a prediction can be made in seconds to minutes on a TPU or a GPU. This opens the door to making predictions at a scale that matches the enormous number of known protein sequences. We developed AlphaFold with TensorFlow 1. As we were migrating away from TensorFlow 1, we decided to use JAX. JAX is also what we use when we open source the model for the whole world to use. We also have a version of AlphaFold that runs using Colab, allowing anyone to run it using minimal setup. So, how can you access AlphaFold? After sharing an outline of our advances at the CASP 14 conference last December, in July we published a detailed paper describing our methods. With this paper, we open source AlphaFold written in JAX with the full model parameters and code. This allows anyone to run AlphaFold on a protein sequence of their choice and has already been used by a huge number of researchers to study their proteins. We also release predictions for all human proteins, plus 20 other biologically important organisms, in the AlphaFold protein structure database. This is freely available for anyone to use. We're thrilled to see the impact that AlphaFold has already had, excited to see where people use it next, and are looking forward to the future advances enabled by the Google ML ecosystem.
Hi, I'm Janine Banks, Vice President of Google's core third-party developer products. We're humbled that you trust the Google ML ecosystem with your experiments and your products, which brings me to the foundation of what we're building, and that's you, our community. This past year, we found ways to connect virtually all around the world, like at Google I/O, where you all started over 9,000 chats in the TensorFlow Adventure Dome. We love connecting with you, and we can't wait until we can all get back to on the road together for in-person events. Until then, we want to continue to provide ways that we can all connect safely. A question we often get is, how do I get started with the community or meet other people to start projects? Well, the first thing you can do is reach out to our group of 175 Google developer experts for ML. They give tech talks, they organize workshops, and they can help you get started. I want to give special recognition to Sayak Paul, a Google developer expert who has been very active in our ML community. He's made contributions to models and tutorials in Tensorflow Lite and for dual deployments on Vertex Ai. Thank you to Sayak and all of our Google developer experts for their amazing contributions. Another great way to contribute is by joining a TensorFlow user group. We have 87 user groups spanning 37 countries, and they hosted great activities this past year, like our group in Santiago, Chile, which recently gave a tech talk on how to generate a model capable of being in the top 1% of the Kaggle leaderboard. The community also continues to grow through the official TensorFlow Forum that we launched earlier this year. We're delighted to see developers sharing ideas and best practices with each other. To date, we've seen over 2,000 users join, making over 9,000 posts. We'd love to have you join the conversation at discuss.tensorflow.org. We want to make the community as vibrant as possible, where anybody is welcome and anyone can gain ML skills. That's why we invest in education, and I'm extremely proud to see we passed the 1 million learners mark across our online courses. Visit tensorflow.org to explore books, courses, and videos to help you improve your knowledge of machine learning. We also have an annual program of faculty awards to support machine learning courses, diversity, and inclusion. This past year, we gave grants to 40 universities in 20 countries to help them develop new machine learning classes. When you're ready to showcase your proficiency in building models, you can take our certificate exam. A year ago, we launched the TensorFlow Developer Certificate. And since then, more than 4,000 developers from over 80 countries have been certified. You can share your expertise with the world by displaying your certificate on social media like LinkedIn and GitHub, or the TensorFlow Certificate Network. We're hearing great feedback, including from Tia, a certified TensorFlow developer who re-entered the workforce after years of being a stay-at-home parent. If you're looking to apply your ML skills or pick up a new skill, we highly encourage you to join Kaggle, the world's largest data science community. It's best known for its world-class machine learning competitions, but Kaggle offers a wealth of resources too for data scientists of all levels, including 110,000 public data sets and 500,000 data science notebooks. Also, dozens of free micro courses. Be sure to check out this notebook written by Kaggle Grandmaster Andrada Oltionu. She details all of the practical resources and routines that have helped her grow from a beginner to a grandmaster in less than 2 years. It's helpful for learners at all stages. Many of you have made our ML tools what they are today. And on behalf of the ML teams at Google, I want to say thank you. As you saw today, there are many ways you can connect, learn, and contribute. We work together with members of the community so you all can build and have an impact on the world. And we hope what you saw here today will help you build the best ML-powered apps or further your research, no matter what stage you're at. Stay tuned for other great talks today, including a deep dive on what's new in on-device machine learning, an overview of the Responsible AI Toolkit, and a closer look at TPUs and how Edge Impulse makes ML accessible to embedded engineers. Make sure you ask all of your burning questions in our live chat. We want to hear from you. Thank you all again for helping build our wonderful machine learning community. It's your stories from the community that continues to inspire us. Let me share one of my favorite stories with you. At Herodox, machine learning has become a vital tool in the advancement of accessible human rights information. Take a look.
UPR Info is a non-governmental organization that works to promote human rights through the Universal Periodic Review. Every 5 years, UN member states make recommendations to other states to suggest how to improve the human rights situation in their country. And with 42 states being reviewed each year, there could be up to 8,000 recommendations that need sorting. This is where UPR Info's team comes in. We extract the recommendations and one by one, categorize them by topic. Having access to information through our database empowers human rights advocates to put pressure on the states and to make them accountable on their human rights obligations. All this work happens with a very small team, and the amount of information is huge. Let's say that we felt the pressure.
Herodox is a non-governmental organization that was founded in 1982. Using the power of machine learning, we're helping UPR Info to better organize and mobilize the thousands of UPR recommendations that are being made. And coincidentally, we just work right across the hall from each other.
We started off with BERT, which is a pre-trained natural language processing model that's available for anyone on Tensorflow Hub. That's really helpful because a ton of work and processing power went into creating this model, and we could build on top of it for our specific use case. We used TensorFlow to build a classifier that would take human rights-related text and assign human rights topics to them. And we had 60,000 hand-labeled examples from the UPR Info team that we could use as training data.
Right now, UPR Info has to explicitly accept or reject a suggestion, and that information is then used to retrain the algorithm. So over time, those suggestions get better.
Updating the database after each cycle has gone from taking 2 to 3 months to taking 1 week.
The first amazing feeling was to catch up with the backlog. That really was a good feeling. This is so much more than sorting out or reviewing recommendations. It's really providing tools for human rights advocates.
It's really been amazing to see how a technology like machine learning can be applied to human rights and have a real impact.
There's always more to do. There's so much more to do. There's so much more potential for positive human rights change. So it's also what's next. What more can we do? That's a motivation, frankly.
Hi, my name is Yuchen Lin, and I'm a software engineer in Google. Today we are excited to talk about on-device machine learning and share some of our newest updates. But what is on-device machine learning? Google offers a range of machine learning solutions to enable running TensorFlow models on your mobile phones, including Android and iOS, web, and even microcontrollers. Turnkey solutions are easy to use, production-ready APIs to tackle common machine learning tasks. You should start with turnkey solutions and see if they meet your needs. For more custom use cases, we help you to train and optimize your model, integrate it in your app, and deploy it in production. We offer easy-to-use production APIs through the MLKit SDK as turnkey solutions. MLKit offers a variety of vision and natural language APIs covering common cases such as barcode scanning and language identification. We are continually adding new APIs and updating our existing ones, so you can be assured that you will always have the latest and greatest features that Google has to offer. Let me go over a few recent updates in MLKit. You can recognize and extract text from images using MLKit's text recognition API. We added new language support for Chinese, Devanagari, Japanese, and Korean scripts. Text recognition now also offers deep paragraphing support to group text into meaningful blocks. We have also improved the quality of MLKit's barcode scanning, including recall, long-tail latency, low-quality image tolerance, and bounding box stability. The MLKit pose detection API helps detect human pose in real time from a continuous video or static image. We have updated the pose detection model to support 3D points for depth analysis. To support language identification, we added an unbundled version backed by Google Play service on Android and reduced the impact on APK size by about 500 kilobytes. If you are developing mobile apps, I strongly recommend you to try out MLKit and add some cool machine learning features into your app. For users in need of custom solutions, we offer both pre-trained model and tools to train, optimize, and deploy your own model using TensorFlow Lite. Let me quickly introduce TensorFlow Lite. TensorFlow Lite is Google's machine learning framework for mobile devices and other edge devices such as browser, microcontroller, and it also runs on desktops. A lot of features of MLKit that I just mentioned are built on top of TensorFlow Lite. In the rest of the talk, we will share many recent improvements of TensorFlow Lite. The first thing I want to talk about is on-device training. TensorFlow Lite was originally designed for an on-device machine learning inference framework. I am proud to share our recent progress for the on-device training support. Now you can train your machine learning model on mobile and other edge devices using TensorFlow Lite. It enables important use cases like on-device personalization, to customize models based on individual user needs without sending the data to the server. It is also an important foundation piece for advanced techniques like federated learning. To demonstrate the on-device training capability, we built an Android demo app for image classification. In the app, we can take pictures from 4 different categories, perform training, and use the app to classify camera inputs. Everything happens on device. Let me show you how it works. To use the demo app to train an image classifier on device, we recommend to take at least 10 photos for each of the 4 classes. In this demonstration, I want to build an image classifier for orange, plant, water bottle, and scissors. I'm taking a few photos on the orange with different angles using the triangle button for the first class. The same for the plant with the circle button for the second class. Water bottle with the cross button for the third class. Scissors with the square button for the fourth class. After collecting the training data, I can tap the train button. You can see that loss is going down with the training process. After training is done, I can switch to the inference mode. If I point the camera to the orange, the model knows it's the first class by highlighting the first button. Plant is the second class. Water bottle is the third class. And scissors is the fourth class. The demo app we built is pretty simple, but you can use your creativity to build other cool apps using the on-device training feature. The demo app and its source code can be found on the TensorFlow Lite on-device training page. To perform on-device training, we need to execute different functionalities like training and inference. To achieve this, you can build a TensorFlow model with multiple TensorFlow functions. For example, in our demo app, we defined a train function that trains the model with training data, an infer function that invokes the model inference, save and restore functions that saves and restores the trainable weights with the file system. After that, you can convert your TensorFlow model to TensorFlow Lite format, integrate the model into your iOS and Android app, invoke the model training in the app that's very similar to what you need to do with the model inference. You can also find the complete codec example in the TensorFlow Lite on-device training page. In detail, the on-device training is supported by implementing a bunch of low-level features. For example, we supported variables to be able to store trainable weights. We supported multiple signatures to be able to run different functionalities like training and inference. We supported gradients for computing the backward path and optimizers to update the weights. The nice thing is many of these features are useful outside of the on-device training as well. You can now use variables for stateful inference or ship a model with multiple different functionalities with the multiple signature support. Currently, some of these features are achieved by reusing TensorFlow kernels with the Select TensorFlow Apps feature. And we are working on supporting more features in TensorFlow Lite natively to deliver an even better performance and smaller binary size. Thank you, and I will hand over to Arun to talk about more exciting updates.
Thank you, YC. Hi, everybody. My name is Arun Venkatesan, and I'm the product manager for the TensorFlow Lite and the TensorFlow Model Optimization Toolkit teams. We have made it easier for Android users to deploy TensorFlow Lite. To reduce Android app size and enable automatic future updates, we had announced at Google I/O 21 that the TensorFlow Lite runtime is being added to Google Play services on Android devices. We are happy to share with you that a few Google apps and frameworks are already using this feature in production, while others are in the process of integrating with it. You can now sign up for the Early Access program to use this feature in your own Android apps. You will still continue to have the option to bundle TensorFlow Lite inside your app. Speaking of deployment, we had earlier announced support to run TensorFlow Lite models on the browser without having to further convert the model to another format. This enables code and model pipeline reuse and eliminates the need to maintain a separate JavaScript codebase. We hope that you're already leveraging this feature. We recently extended support to also run quantized TensorFlow Lite models on the browser, resulting in improved latency and smaller model size. We will talk more about quantization in a later part of this presentation. Machine learning models running on device need to be highly performant in order to deliver a great user experience. We continue to offer the best out-of-the-box performance on CPUs, as well as peak performance using on-device accelerators. XNNPack is a highly optimized library that enables faster CPU performance of TensorFlow Lite models via highly optimized implementation of floating point ops for ARM, WebAssembly, and x86 platforms. XNNPack is now turned on by default, starting with TensorFlow version 2.7. XNNPack also supports quantized TensorFlow Lite models, resulting in an approximately 30% speedup on ARM64 mobile devices and a 5x speedup on x86 laptop and desktop systems for certain image models. Mobile and other edge devices have limited computational resources, memory, and storage. So it's important to keep your application resource efficient. You can optimize your TensorFlow Lite models to be smaller, run faster, and be more energy efficient using techniques and tools in the Model Optimization Toolkit. Pruning is one such technique. Pruning removes unnecessary connections between layers of a neural network to produce a sparse model. The pruning APIs have extensive functionality that provide you with tools for model manipulation. These enable control of multiple aspects of model pruning, such as how and when to prune, and also track the progress of pruning. A new extension to the pruning API now allows you to specify which parts of the model to apply the pruning policy to. Let's see this new feature in action. You heard about XNNPack earlier in the presentation. The example here shows how to apply selective pruning to the parts of the model that can be accelerated using XNNPack while leaving the rest of the model untouched. Such selective pruning allows an application to maintain model quality while targeting parts of the model that can be accelerated. Weights and activations occupy the majority of model size and are usually represented as 32-bit floating point numbers. Quantization is a technique to represent weights and activations as 8-bit integers or 16-bit floating point numbers to help reduce the model size with improved latency. However, due to the reduced precision, quantization can potentially result in an accuracy loss. We have released a new set of tools to help you easily debug the accuracy loss due to post-training quantization. The Quantization Debugger makes it possible to do quantization quality metric analysis of the existing model. The debugger logs differences between the float tensors and the quantized tensors for the same op location and emits metrics such as the mean square error between the float and the quantized results. You can easily identify the layers that have the largest error metrics by viewing the Quantization Debugger's output. Once you have identified the problematic layers, you can skip quantizing these layers using selective quantization, potentially resulting in a model with higher accuracy. In order to run a model on device, you first need to convert a TensorFlow model to the TensorFlow Lite flat buffer format. Further, to improve the peak performance of your models, TensorFlow Lite's delegates provides a convenient mechanism for hardware acceleration of TensorFlow Lite models on accelerators such as the GPU. In other words, not only do the ops in your TensorFlow model need to be compatible with TensorFlow Lite, but your model also needs to be compatible with the GPU delegate to be able to run on the GPU. TensorFlow Lite's target-aware authoring tool makes it easy to detect not only TensorFlow model compatibility with TensorFlow Lite, but also tells you if your model is compatible with the GPU delegate. You just need to add a decorator to wrap your TF function model to detect compatibility. Surfacing both the model and accelerator compatibility at authoring time helps model developers avoid the extra work due to the conversion errors, and also provides an opportunity earlier in the model development lifecycle to use GPU-compatible ops in the model. We are now working on extending the target-aware authoring tool to support other on-device accelerators. You can also detect GPU compatibility post-conversion of your TensorFlow model to TensorFlow Lite. Our new model analyzer tool dumps a helpful log of your model structure and highlights potential GPU incompatibilities. State-of-the-art models and reference app help you get started with TensorFlow Lite. We have new models and reference apps to share with you. We recently released the Movenet model, a state-of-the-art post-estimation model that can detect 17 points. We also published reference apps for reinforcement learning and optical character recognition. As a recap, we learned about some of the new updates to our ready-to-use turnkey APIs in MLKit. We saw a demo of on-device training, talked about TensorFlow Lite in Google Play services for your Android apps, performance and optimization updates including techniques and tooling, compatibility tooling, and new state-of-the-art models and reference apps. You can learn more by visiting our website. Do keep in touch with us via GitHub and other public forums. Thank you for your time.
Hi, I'm Tris Warkentin.
And I'm Robert Crow, and we're going to be talking about production ML, TFX, and what's new.
We're really excited to share what we've built in TFX, as well as some of what you, the community, have created. But first, a little background for those of you who might not be familiar with TFX. To begin with, as data scientists or machine learning engineers, we tend to focus on our models. That's natural, because that's where the magic happens. But when we move to production ML, we discover that there's a lot more that's required to be successful. At Google, we've measured the ML model code to be something like 5% of the total code necessary to train and deploy a model in production. But all of the other tools and infrastructure that you see here are critical to success. To put any piece of software into production, to use it in a product or service, we need a production infrastructure and process. First, we need all the things that any ML development needs, along with some special considerations because we're working in a production environment. But we also need all the things that any production software deployment needs. In other words, in addition to ML best practices, we also need to apply DevOps principles and practices to machine learning. We put tons of ML into production at Google, and we needed a strong framework, so we created TFX. You've probably been using it, or rather using products and services that are implemented using TFX. It's used not only at Google, but across all of the Alphabet companies. And since it's open source, it's available for you to use too. This is what I call the hello world of TFX, which is the pipeline that you start with when you just do a pip install. The components on top are a pipeline for training, and the ones on the bottom are a pipeline for running batch inference. On the right side are some deployment targets like TensorFlow Hub, JS, and TensorFlow Lite. Those are for use in a web browser, mobile application, or IoT device. You can also use TensorFlow Serving if you're going to serve your model for online or batch predictions, or Vertex Prediction if you need a cloud-based managed service.
One of the key aspects of TFX is portability. We say that TFX runs just about anywhere, and here's what we mean by that. You can run it in different execution environments, including just running an entire pipeline in a web browser using Colab, or on your notebook, or in a Kubernetes cluster, or in Vertex Ai. You can orchestrate it with a wide variety of orchestration engines, or just plain Python, including Airflow and Kubeflow. And you can perform all of the processing on one machine, like your laptop or a server. Or you can leverage the compute resources of a cluster by using Spark, Flink, or Dataflow. This kind of portability is incredibly powerful because it means that you're not locked into one way of running your pipelines, and you can easily move pipelines to different sets of infrastructure, scaling up from a web browser to a huge cluster with almost no code changes. Okay, so that's TFX. But what's new? Well, we've only got 10 minutes, so let's look at a few highlights. First, there's new stuff in the core TFX SDK, starting with conditional control flow. You can now test and branch, or run optional components based on the current state of pipeline artifacts. So, a good example here is that if you're training a model and the accuracy falls below a certain threshold, you can optionally run an alerting component so that your team is aware of the situation. Another great addition to TFX that a lot of people have been asking for is the new exit handler. This allows you to detect and act on success or failure of your pipeline and components and run custom code based on the status. At the time of this recording, this is scheduled to be available in November 2021, so it might already be there depending on when you're watching this. But remember, TFX is an open source project, so you can contribute too. One of the best ways to get started is to join our special interest group, SIG TFX Add-ons, which brings together community contributors to create new components, tools, libraries, examples, and visualizations to make TFX even better. Let's take a look now at some of the work that the TFX Add-ons team is doing.
A great example is the Firebase Publisher project, which is a TFX component to publish or update models, usually TF Lite models, from TFX to Firebase ML. So you can train TF Lite models for mobile apps with TFX and publish them to Firebase, where you can dynamically serve the latest version of the model and update without pushing a new version of your app to users. Another great example is the load testing project. By adding a load test component to your pipelines, you can run load tests as part of training pipelines before you deploy to production. That allows you to measure serving latency under load to make sure requirements are met before it affects your users. That helps avoid issues early, before they become fire drills. You can also use it during development to measure speed improvements in your models. Yet another great example that really shows the flexibility of TFX is the Xgboost Evaluator project. Xgboost is a very popular framework for building gradient-boosted trees, and this project creates a component to add support for evaluating Xgboost models, which you can train in TFX. One of the things that customers tell us is they need to be able to train models in more than one framework, and this project extends the standard TFX Evaluator component, which helps expand Xgboost support in TFX. Another exciting TFX add-ons project is the Feast Example Gen component. This project is creating a TFX add-on component which allows TFX pipelines to ingest Feast datasets. Feast is the leading open source feature store for machine learning, and it offers low latency online data for real-time prediction and offline data for batch processing, along with the other advantages of using a feature store for your data.
We'd like to give a big shout out to all of the project leaders in the TFX add-ons team, and especially to the leaders of the 4 projects that we've just mentioned. AI and machine learning only advances through the open collaboration of researchers and practitioners worldwide, and community teams continue to be incredibly important to success. Thanks. And don't forget, you can help too by joining TFX add-ons. But if you're just getting started in building ML for production applications, you can also sign up for a 4-course specialization that we're creating with Deep Learning AI and Coursera, working with Andrew Ng, who is teaching the first course in the series. It covers TFX and a whole lot more to help you come up to speed on the state-of-the-art of production ML. For more information, don't forget to visit our website where we have tons of tutorials, examples, and docs. And check out these other resources for even more. That's our talk. Thanks for listening.
Hi, everyone. My name is Parker, and I'm a product manager at Google AI. I'm here with my colleague, Ludo, to talk about how you can build with the Responsible AI Toolkit. Today, we're going to give you a very quick overview of Responsible AI at Google and the Responsible AI Toolkit. We'll then illustrate how 2 of our tools, Fairness Indicators and the Language Interpretability tool, can be helpful in a real-world example. First, it may go without saying that AI is transforming the world we live in. As creators of new products, it's staggering the range of new opportunities created by AI across so many different sectors. And yet, for AI to be truly useful and valuable, it needs to be built, tested, and operated responsibly. At Google, we have a set of principles that guide our approach to responsible AI. These include the 7 listed on this slide, as well as 4 applications of AI that Google will not pursue. We've developed the Responsible AI Toolkit to operationalize these principles at Google. We open-sourced the toolkit a couple of years ago and have been adding resources to it ever since. To better contextualize the toolkit, let's take a look at a typical machine learning workflow. Building AI responsibly means answering hard questions at each step in the lifecycle, from problem definition through to model training, testing, and deployment. While the specific questions that you ask depend on your own unique principles, the tools we've developed are designed to be flexible and to help you answer them. Our Responsible AI Toolkit is a collection of technical resources to help you and your team at each stage in the lifecycle. We encourage you to take a deeper look at these resources online. They include Colab tutorials, documentation, and user guides, which can be accessed via the QR code shown on this slide. Today, we're going to zero in on 2 tools that can help you evaluate and probe your models for unfair bias. We'll introduce the tools in a simple real-world example, which we spoke about in our previous talk at Google I/O this spring. Imagine that you are the owner of a new restaurant chain. Here's the stylish interior of one of your restaurants. After eating, your customers leave online reviews about their experience. As a diligent owner, you decide to use ML to analyze customers' online comments and feedback to assess customer satisfaction and help you come up with new ideas for how you can improve your restaurants. As a first step, you decide to build a sentiment classifier that assesses the degree to which each customer's comment is either positive or negative toward their experience at your restaurant. The inputs to the sentiment classifier are the text body of the review metadata, and any associated images. We have 2 main objectives. First, we want to ensure that our sentiment classifier has high overall accuracy for predicting sentiment. Second, we want to make sure that the classifier does not disproportionately misclassify reviews based on sensitive identity characteristics that may be mentioned in the reviews, for example, like language, gender, or race. We'll first demonstrate how you can use fairness indicators to perform a disaggregated or sliced evaluation of your model's performance to check whether your model is achieving your 2 main objectives. But first, it's worth briefly mentioning why analyzing models for fairness is really hard. First, fairness is highly contextual and almost never reducible to a single statistical definition. In any real-world setting, it's important to acknowledge and embrace this fact and explore multiple qualitative definitions and statistical measures of fairness. Second, Fairness testing requires iterating with a large number of stakeholders. So you need mechanisms that make it easy to share the results of evaluations with others. Thirdly, many real-world ML systems operate at very large scale, so you need tooling that allows you to evaluate your model on large data sets and as part of repeatable pipelines. Fairness indicators can help you solve some of these challenges. First, fairness indicators makes it easy to zero in on the performance of your model for specific subgroups or demographics. It also comes preloaded with some of the most common fairness metrics, which means you don't have to commit to a single definition up front. Second, fairness indicators provides an interactive UI and dashboard for exploring and sharing the results of your analyses with others. Here is a snapshot of the fairness indicators dashboard. Within the dashboard, you can select one or multiple fairness metrics, select which slices or subgroups you want to review, set different decision thresholds, and review and share output as charts and tables. Lastly, Fairness Indicators is scalable and flexible. It can be run as part of TFX's Evaluator component, as a TensorBoard plugin, or as standalone binaries. It also supports both TensorFlow and non-TensorFlow models. With that background, let's return to our restaurant review classifier example. We can use fairness indicators to evaluate our first objective, which is accuracy. We use the presence of gender identity terms as the category in question for our sliced analysis. We wouldn't want the presence of these terms to unduly influence the outcome of the classifier. Fairness indicators shows us that reviews containing terms implying certain genders actually have a lower accuracy than other reviews, which is concerning. Now we turn to our second objective, which is to minimize any differences in error rates, and specifically false positive rates. This graph shows us that reviews containing terms that imply certain genders tend to have a higher FPR than other reviews, especially for the male gender. This means that they are far more likely to be classified incorrectly as positive, which could lead to biased, misleading conclusions for your assessment efforts. Now that we've identified a couple of issues with our model, we can take this slice of our data, in this case, customer reviews that contain gendered terms, and we can use another tool from the Responsible AI Toolkit, called the Language Interpretability tool, to do an in-depth analysis of the model's performance. Ludo, over to you.
Thank you, Parker. Now we can use the Language Interpretability tool, Lit, to further investigate these findings. Lit is complementary to fairness indicators and serves a different purpose. It's not about inspecting average global metrics on the whole dataset, but it allows you to build intuition about the model prediction patterns by interactively inspecting the model, often starting at data point level. Since the last Lit demo at Google I/O, we have made good progress, and we want to share that with you today. Let's keep building on our I/O example. This is the Lit UI with all modules visible. It can be intimidating, but the tool is fully modular, and you can choose different views with the module you need. Think of it as a toolbox to inspect your model. For clarity, we'll only zoom on specific modules in the next slide. The data table module displays your dataset in the UI, and here we see all the restaurant reviews in your dataset. Lit also allows you to tweak the text and evaluate examples side by side, a concept known as Counterfactual Testing. Let's try this for the data point selected here, a seemingly sarcastic negative review. Let's change the gender reference in this sentence. In Lit, you can edit the data point directly in the UI and add it to the dataset, and compare the old and the new versions. The bar graph shows that the classifier considers a sentence with waitress more likely to be negative sentiments than the identical one with waiter, even though these words probably shouldn't bear impact on sentiment. Lit allows to use silency methods like lime or integrated gradient that indicate how much each word accounts for the model's prediction. The identity term waiter and waitress are darker in color than the surrounding words, indicating that they have a stronger prediction power. This could be one of the hidden causes behind the disparities we surfaced in fairness indicator. But we can do further probing. Beyond just comparing single points, you can edit a batch of data points. The model seems to be influenced by the gender noun waitress, but does it react to gender pronouns too? We'll change all the masculine personal pronouns to feminine ones. We can now look at the 19 pairs of similar data points with different pronouns. We notice that on sentences with many tokens, the prediction doesn't change based on pronoun. But when the sentence is short, like this one with only 3 tokens including the pronoun, the model does make a difference between the two examples. This might be an interesting insight when you test this model before launch. So you think of testing with shorter sentence. So far, we looked at how to interpret a model using an input feature like the noun waitress. But we know that there are many other words that represent this notion of gender. What if you're more interested in how this notion of female gender concept influences the model in general? TCAV is a method developed at Google Brain by Bin Kim and others that can help you do this. TCAV shows how important a high-level concept like the female gender is for prediction class. And you can do this after training without even thought of the concept of gender before training. To capture the impact of a gender concept, Lite creates a concept activation vector, or CAV, from our selection of data points exemplifying that concept. Here, for instance, we can group together sentences with female pronouns as well as various females-oriented nouns. It is important to carefully think of how you build your vector for it to be representative of this high-level concept you're trying to capture. Once you have this vector, we calculate the CAV score. Here we can see that the concept of female gender represented by my CAV is indeed influencing my model, because the CAV score is high and statistically significant. Look at the blue score bar. It's below the gray baseline. This means that the female gender is contributing to the negative sentiment classification. TCAV is a powerful method when your goal is to get intuitive and global behavior characteristic of a model. To build relevant CAVs, we recommend that you read our website and documentation. We are pleased to announce that we're releasing today our new version of Lite. On top of TCAV, it includes some preliminary features for image and tabular data, and you can find more in our documentation. You can use Lite with your own models and data by installing the pip package LiteNLP. Lite is framework agnostic. You can use it in TF or other frameworks, and in many surfaces like notebooks or running as a standalone server. Lite is also model agnostic. It works with classifier, regression, seek-to-seek, and other model tasks. To set it up with your own model, you need to define a Lite model that can make prediction based on a given input, which is defined in the input spec, which in this case includes the text review and the ground truth sentiment label. The output spec defines the model output, which in this case a classification score with 0 for negative sentiment and 1 for positive sentiment. For your data, Lite has been primarily designed for text, but we have preliminary feature, as I just said, working now for image and tabular data too. To set it up with your own data, you need to create a Lite dataset class that loads your data into memory and specify the name and types of all the features in the dataset. There are many more tools than the ones we mentioned today in the Responsible AI Toolkit, which collectively represent the work of many teams across Responsible AI. We encourage you to check them out and talk about Responsible AI questions at the new Tensorflow Forum. Please don't hesitate to reach out to us if you have any question or feedback. Thank you.
Hi, my name is Jake Vanderplas. I am a software engineer at Google Research, and today I want to tell you about JAX, which is a Python package for accelerating your machine learning research. So at a glance, what is JAX? Basically, JAX provides a lightweight API for array-based computing that's very similar to NumPy. So if you're writing NumPy code in Python already, JAX will probably feel very familiar. On top of that, what it adds is a set of composable function transformations for doing things like automatic differentiation, just-in-time compilation, and then automated vectorization and parallelization of your code. And then finally, what you can do with this code once you write it is execute it on CPU or GPU or TPU without any changes to your code. So it ends up being a very powerful system for building models from scratch and exploring different machine learning problems. On top of this, JAX is really fast. In the recent MLPerf competition, which pitted different software and hardware systems against each other on common deep learning algorithms and problems, JAX outperformed other systems on some of these common problems. You can take a look at these results and see how JAX stacks up against some of your other favorite systems. So let's step back and motivate JAX a little bit. Thinking about this, how might you implement a performant and a scalable deep neural network from scratch in Python? Usually, Python programmers would start with something like NumPy because it's this familiar array-based data processing language that's been used literally for decades in the Python community. And if you were trying to create a deep learning system in NumPy, you might start with a predict method. Here, this is a feed-forward neural network that does a sequence of dot products and activation functions to transform the inputs into some sort of outputs that can be learned. The next thing you need once you have this model defined is a loss function. And this is the thing that'll give you your metric that you're trying to optimize in order to fit the best machine learning model. So here we're using a mean squared error loss. And now what's missing with this deep learning in NumPy? Deep learning takes a lot of computation. We'd like to run it on accelerated hardware. So you want to run this model on GPU and TPU. And that's a little bit difficult with classic NumPy. The next thing you might want to do is use automatic differentiation, which would let you fit this loss function very efficiently without having to do numerical differentiation along the way. Next thing you might want to do is add compilation so you can fuse together these operations and make them much more efficient. And finally, if you're working with large data sets, it's nice to be able to parallelize this operation across multiple cores or multiple machines. So let's take a look at what JAX can do to fill in these missing pieces. The first thing you can do is replace the NumPy import with jax.numpy. And this has the same API as the classic NumPy in many cases, but it will allow you to do some of these things that were missing in the first pass. So for example, JAX automatically via this XLA backend will target CPUs, GPUs, and TPUs for fast computation of your models and your algorithms. On top of that, JAX provides this set of composable transformations, one of which is the grad transform, which can take a loss function like MSE loss and convert it into a Python function that computes the gradient. And now, once you have this gradient function, you might want to apply it across multiple pieces of data. And in JAX, you no longer have to rewrite your prediction and your loss functions to handle this batch data. If you pass it through the VMAP transform, this will automatically vectorize your code, so you can use the same code across multiple batches. If you want to compile this, you can use the JIT transform, which stands for just-in-time compilation. And this will fuse operations together using the XLA compiler to make your code sometimes much, much faster than it was originally. And finally, if you want to parallelize your code, there's a transform that's very similar to VMAP that is called PMAP. And if you run PMAP through your code, this will be able to natively target multiple cores in your system or a cluster of TPUs or GPUs that you have access to. So this ends up being a very powerful system to build up these fast computations without much extra code. So the key ideas here is in JAX, Python code is traced to an intermediate representation. And JAX knows how to transform this intermediate representation. And I'll tell you a little bit about this in a moment. The same intermediate representation enables domain-specific compilation via XLA, so you can target different backends. It has this familiar user-facing API based on NumPy and SciPy. So if you've been coding in the Python data space for a while, JAX should feel fairly familiar. And on top of it, it's this powerful set of transforms, the grad, JIT, VMAP, PMAP, and others that let you do things with your code that you weren't able to do before. So I want to step back a bit now and talk about how JAX works, because it's interesting to use a powerful black box like this, but I think it's even more fun if you know what's going on under the hood. And the gist of how JAX works is that it traces Python functions. So just as a thought experiment, let's take a look at this function, f of x return x plus 2. What does this function do? You know, it may seem obvious, but Python is such a dynamic language that this function could literally do anything. You know, say if x is an instance of this espresso maker object that overloads the add function so that when you tell it the number of espressos you want, it'll SSH to your espresso maker and make those automatically. This is a little bit silly, but it just drives home the point that we don't really know what Python functions do unless we know exactly what's being passed to them. And JAX takes advantage of this Python dynamism in order to figure out what's going on in a function and to come up with a representation that can be transformed in the way that we saw earlier. So it does this by calling the function on what's called a tracer value. So an example of this is a shaped array tracer value. And you can see what happens here is that the add function not only returns a shaped array with the result, but also records the computation. This isn't exactly what's happening in the JAX code, but it's the basic gist of what's happening under the hood. So how does this work? So let's say you have a function like this that computes the base 2 log of a number x. How does JAX trace this and understand what's going on? Well, the first thing is all of JAX operations are based on operations in lax, which is this set of primitive operations that mirrors XLA. And now when we want to compute the log base 2 of some array, the first thing we do is put in a shaped array value in place of this x. And once that shaped array value is in there, we can step through the function and see what operations are done on this. So we see the log of x and we record b equals log a. We see the log of 2 and we record c equals log 2. We see the division operation between these two and we record d as division of b and c. And then we return this d value. And now what's left here is what's known as a JAXper, short for a JAX expression or JAX representation of the function. And this encodes everything that this function does in terms of its numerical processing of the inputs and how they lead to the outputs. And this is a well-defined intermediate representation that lets you do a number of things. JAX knows how to automatically differentiate this, knows how to vectorize and parallelize this, and it knows how to just-in-time compile this by passing this to XLA. And so the result is you have this nice pipeline where you're writing Python code on the left, and JAX is tracing it, turning it into an intermediate representation, transforming that intermediate representation in the way that you specify in your Python code, and eventually JIT compiling it to HLO, which stands for high-level optimized code, which is what XLA reads in. And XLA can take this HLO, compile it, and send it to CPUs, GPUs, or TPUs. And all that you need to do as a user is write this Python code on the left-hand side. Everything else is under the hood and kind of happens automatically. So this has been really powerful for use across Google and outside Google as well. These are just a couple of examples of applications that JAX has powered. On the top left, we have protein folding. This is the AlphaFold from DeepMind. The current version of AlphaFold runs on JAX. I won't say much more about that because there's another talk in this session that dives into it. But we've also seen JAX used for robotic control, used for physical simulations and other simulations where you need to run lots of computations on accelerated chips. And it ends up being an incredibly powerful system for exploring and building these kinds of models. So if you'd like to get started with JAX, you can go to our website. There's a very nice getting started guide, a 101 tutorial to help familiarize you with how to get started with JAX. And if you want to dive in a little more, there's a whole ecosystem of tools built around JAX for everything from deep learning. There's higher level deep learning libraries. There are optimization libraries for doing physical modeling and other applications. Probabilistic programming, there's graph neural networks, and many, many more that I don't have time to highlight here. And with that, I'd like to thank you for listening to this talk. If you want to learn more about JAX, take a look at the documentation at jax.readthedocs.io. And we'd love to see what you build with this tool.
So with me today are Jenny and Jan from Edge Impulse. And that's a company that makes it easy for you to develop with TinyML. And one of my favorite things about Edge is that you have a very large and active developer community. Could you share with us a little bit about how many projects they've completed with Edge Impulse so far?
So we just crossed, about a week ago during a conference, we crossed 40,000 projects, which is an astonishing number. And it's amazing the type of stuff that people build once you give them kind of the tools, right?
Congrats, that's really fast growth. And could you share how Edge makes it easy for developers to develop with TinyML?
So Edge Impulse makes it really, really easy for an embedded developer or any other developer to take the sensor data or any other type of data that they have such a strong knowledge of, upload that into our tool, and we have other things involved like AutoML to help you figure out exactly what type of model you need to use in order to successfully use that data with machine learning. And that's completely without needing to write any code. So you don't need to be a Python developer to use Edge Impulse, especially if you really only know something like C++.
The biggest thing is we are an engineering tool, and we want to put power into the hands of the people that really understand the data. So for us, everything starts, I like to say it when people onboard, is that everything starts with data. So we try to help these people actually gather data from the field, and use that first to get insight in what they have. And then they're the domain experts. They can actually tell us what is good and what is wrong. And the only thing we can do is just give them the tools to make that decision quickly. So the big thing about Edge Impulse that lets you build applications and machine learning models from scratch with your own data, rather than just downloading them from a model zoo. So with that, you can build applications that respond to your voice, for example, like whenever I say, TinyML. So that is actually trained on 46 minutes of data only that we actually collected, not in the office, but live during a conference. So during the TinyML Summit, we gave a QR code to people. They record a little bit of their voice. We cut it up into data samples and train a model with that. So here we have our whole data set, 46 minutes in the test set. And we can actually show our Feature Explorer to see if that data separates and how well that actually works. So here we have the three classes that we have: noise, background noise, unknown, different keywords, and the TinyML sentence. And you see a really nice cluster of green data here on the right with all of our samples. And once we see clusters going into each other, here we have some overlap of blue noise and green TinyML. Those are samples we probably want to look into. But with this small amount of data, we managed to train a 96.6% accurate on our training set and about 94% on our test set, just with a small amount of data. And the Feature Explorer helps us here as well, so we can dive in and see exactly which of these samples were classified correctly and which ones were classified incorrectly. Once again, giving us some insight in the dataset quality. And there's two ways of actually programming a neural network out. So we have our visual modes, which is really convenient. We'll load stuff that we know is going to work for your dataset and your problem. But if you want to have the full power of TensorFlow and Keras in your hands, just go to the expert mode, as seen here, and you'll have full freedom in the way that you design your neural networks.
Thanks, that's really cool. And where can developers go to learn more about Edge Impulse?
Developers can sign up for free at edgeimpulse.com, and you can also get started from our documentation at docs.edgeimpulse.com.
Yeah, so we have end-to-end tutorials on anything from doing stuff with vibrational data, rebuilding this keyword spotting model that you saw earlier, image classification, wherever you want to run it. And the cool part is that we have launched not one, but two Coursera courses together with Sean Heimel. The first one, I think, has over 10,000 already enrolled. That literally guides you to everything you need to know about embedded machine learning. And the second one about how you can do embedded machine learning for vision applications.
Thank you both. Your demos look awesome, and I really appreciate you joining us.
Hello, my name is Yue Feng. I'm going to talk about TF.Distribute, TensorFlow's distributed training library. TF.Distribute requires minimum code changes to scale up your training. It allows a unified workflow across different hardware, different training architectures, with great out-of-box performance. We released this library in 2018 with Mirror Strategy, which provides multi-GPU synchronous training. It does data parallel training as it replicates model variables and computations on all the GPUs. All GPUs run in lockstep and use all-reduced to aggregate gradients. Multi-worker mirrored strategy is similar to mirrored strategy, but it supports synchronous training on GPUs on multiple hosts. We have also developed Tpu strategy. It supports synchronous training on Tpu chips. It has been a couple years since our first release. We are still actively working on it. The next strategy I'm going to introduce is parameter server strategy. It supports parameter server training, which is a common data parallel method for asynchronous training. When do we use parameter server strategy? It has its own use cases. If you want asynchronous training to get a larger training throughput, or if your model has large embeddings, or if your workers can be frequently preempted, you should consider using parameter server strategy. So what is parameter server training? In this approach, variables are stored on dedicated servers called parameter servers, shared by all training workers. Most of the computation happens on these workers. In each training step, workers pull the latest variable values from parameter servers, run forward, backward paths with their own training data, then send back gradients to parameter servers. Each worker completes a training step on their own. They update the variables on parameter servers independently. This is why we call it asynchronous training. It is scalable and can tolerate worker failure. In TensorFlow 2, we've adopted a very different approach to implement parameter server training. We call it single client setup. In this setup, the user program will run on the coordinator. Workers and the parameter servers run a standard TensorFlow server, which passively executes requests dispatched from the coordinator. We have also developed a set of new APIs to support this setup. Let's see how we can use parameter server strategy with customer training loop. This is a customer training loop with mirror strategy. We create a model and optimizer on the strategy.scope. We create a dataset, a training step, wrapped into a TF function and the training loop. To switch it to parameter server strategy, we need to make some changes. We create a parameter server strategy and a cluster coordinator with a strategy object. Similarly, we created a model and an optimizer on the strategy.scope. We created datasets using the coordinators create per worker dataset method. We still have the step function wrapped into a TF function, but we use coordinator.schedule to dispatch this function from the coordinator to workers. The last part is to do coordinator.join, which waits until all scheduled functions are executed. Parameter server strategy has also integrated with Keras model.fit. This is how we use mirror strategy with Keras model.fit. To use it with parameter server strategy, you will just need to replace mirror strategy with parameter server strategy. The rest is exactly the same. Here are some resources for TF.distribute and parameter server training. We have also provided guides and tutorials on how to migrate from Estimate and Tpu Estimate to TF.distribute. Thank you.
Hi, my name is Shaheen. I'm an engineering manager here at Google, and today I'm going to tell you about Google's Cloud TPUs. One of many challenges that companies are facing to train ML models is that the state-of-the-art in machine learning models is growing very fast. As a result, there is a need for training models faster than ever before. In order to achieve this speed up, there are 3 approaches that have proven to be useful. First, using specialized hardware for machine learning. Google has developed the TPUs with a custom design particularly for machine learning workloads. Second, the ability to scale your training on many accelerators in parallel. Distributed training on thousands of accelerators has proven to be a great technique for reducing the overall training time of ML models. And third, the software stack that is able to take advantage of such a scale of distributed accelerators is an important part of success in training models faster than ever before. Let's look at the TPU and Tpu Pods. The Cloud Tpu V4 became generally available on GCP in January 2019. Since then, many customers have taken advantage of these machines in the cloud. Also, the Tpu V4 pod has enabled customers to use 100 petaflops of compute power in GCP. Sundar recently announced our latest TPU generation, the Tpu V4 at Google I/O. These machines are powered by the V4 chip, which is more than twice as fast as the V3 chips. Like the Tpu V3, the Tpu V4s are connected together into supercomputers called pods. A single V4 pod contains 4,096 V4 chips, and each pod has 10x the interconnect bandwidth per chip at a scale compared to any other networking technology. This makes it possible for a Tpu V4 pod to deliver more than 1 exaflop per second of computing power. Next, let's talk about the distributed training using thousands of TPUs. The latest results of MLPerf, which were published in June this year, included a submission using Tpu V4 pods for ResNet 50, which was the fastest time to train the model at just 14 seconds. As a comparison, when the original paper was published in 2015, the time to train the model was about 29 hours on GPUs. The winning submission from Google is using more than 3,400 chips to train ResNet 50. In fact, across many tasks in MLPerf, including rankings and recommendations, as well as natural language processing, Tpu V4s have demonstrated speedups over fastest submissions from the industry. If you are interested in the full MLPerf results, I invite you to take a look at our blog post that goes into more details about the submission. Now, let's talk about the flexible software that enables interactive supercomputing on this platform. Regardless of your ML framework of choice, Cloud TPUs can help you achieve the best performance for training your model. So whether you're using TensorFlow, PyTorch, or JAX, the best and easiest APIs are available to train your model. A typical Cloud TPU development workflow may consist of starting with one of many open source reference models or developing a model with your own code. Next, you would use a single TPU device to test for functionality and correctness of your code and validate your desired performance metrics. Once you have this model ready, you can start by moving to a larger TPU pod slice, say a V332, by verifying that your hyperparameters are still good for larger scale training and to ensure that you can obtain linear or close to linear scalability. Depending on your model and your desired performance targets, you can then increase the slice size to a full pod or to the limit that your model allows. TensorFlow has introduced the Distribution Strategies API, which allows you to write cross-compatible code for a wide variety of hardware configurations, such as TPUs, TPU pods, GPUs, as well as multi-GPU machines. As you can see, with only a few lines of code, you can detect the hardware and select the appropriate distribution strategy. TPU strategy for TPUs or TPU pods, mirrored strategy for GPUs or multi-GPU machines. To use a distribution strategy, instantiate your model in the strategy scope, and you are done. The rest is regular Keras code. You can also try it out with the Colab sample at bit.ly/keras-tpu. While training, the batches are automatically split between the TPU cores. As you perform the hyperparameter tuning, you can use settings from the strategy that would allow the optimum batch size as well as learning rate. Notice that the compile fit calls are the same as normal Keras code. To improve performance, you would set step per execution higher than 1, say to hundreds of steps, knowing that the per batch callbacks would only be executed every hundreds of batches. Another major feature of the Cloud TPUs that makes the user experience incredibly smooth is the new Tpu Vm Experience. In the past, for using TPUs on cloud, a network-attached architecture was used. The user would connect to a VM and then interact with the TPUs through gRPC calls. This was difficult to debug and sometimes introduced delays in the experience. With the all-new Tpu Vm architecture, you have root access to every Tpu Vm you create, so you can install and run any code you wish in a tight loop with your Tpu accelerators. You can use local storage, execute custom code in your input pipelines, and more easily integrate Cloud TPUs into your research and production workflows. I'm excited to say that the Cloud Tpu V4 with the Tpu Vm architecture will be available in GCP this quarter. If you're interested in early access, please contact Google Cloud Support. Remember, you can always get in touch by visiting g.co/cloudtpu.
Hi, I'm Anna, and Azalia and I are very excited to tell you about our work on machine learning for chip design. Our motivation in this work was the observation that advances in systems and hardware have fueled massive progress in machine learning. And we believe it's time for machine learning to return the favor and transform the way in which we design systems and hardware and close the loop. Some key takeaways from this talk: we're going to describe a deep reinforcement learning method that is capable of outperforming or matching human expert performance on the task of chip floor planning. This method can generate superhuman chip layouts in under 6 hours, whereas human experts take weeks or months at an extremely high cost. And superhuman layouts generated by this method were used in Google's latest AI accelerator, Tpu, which was taped out earlier this year. And we recently published this work in Nature. So what is the chip floor planning problem? At a high level, it's just a form of graph resource optimization. So we take as input a graph of chip components, memory components like macros, and logic gates like NAND and NOR, all of which are connected by wires. And the objective is to place this graph onto a 2D chip canvas such that we minimize various costs, like latency of computation with this circuit, power consumption, area, while adhering to hard constraints like routing congestion and cell utilization. But this is an extremely complex problem. So compared to previous towering challenges in AI like chess and Go, a simplified version of a single instance of the chip floor planning problem has 10 to the 9,000 possible states. And there has been 60 years of research on this topic. Prior approaches fell into 3 broad categories: partitioning-based methods like min-cut, stochastic or hill-climbing-based approaches like simulated annealing, and analytic solvers like the prior state-of-the-art replace. And in this work, we propose a 4th category of approach, learning-based methods. So more specifically, we take a deep reinforcement learning approach to the chip floor planning problem, where we train an agent to place the nodes of this chip netlist graph one at a time onto the canvas, and after placing all these nodes, we get an approximate reward signal that we use to punish or reward the policy and get better and better at placing chips over time. So just to make this a bit more concrete, at each time step, the state is a representation of the chip netlist, a representation of the current node to place next, and a representation of the canvas onto which we need to place that node. The action is the decision about where to place that node onto this grid, and the reward is, after placing all the nodes, a weighted average of approximate wire length density and routing congestion. And in this work, we take a hybrid approach to placement optimization. So the RL agent places the macros, or these larger memory components, onto the canvas, and then we use a force-directed method to place the standard cells so that we can quickly evaluate the quality of this placement. So here are some results on a Tpu V4 block. Unfortunately, we have to blur these images due to confidentiality, but the white regions are macros, the green regions are clouds of standard cells or logic. And as you can see from this image, the machine-learned placement has this more rounded, organic-looking placement, whereas a human expert placement has a very rigid-looking shape. And the interesting thing here is that this rounded shape actually allows the machine-learned placement to minimize the wire length needed to connect the macros or memory components to the logic in the center. And the human expert placement took 6 to 8 weeks to generate, whereas the machine-learned placement took only 24 hours. And we've actually significantly reduced the runtime of our methods since then, and we can now generate placements in under 6 hours. And that's all is going to tell you a little bit more about how we achieved that.
Thanks, Anna. So one of our goals in this project was to be able to train policies that generalize to new unseen chip blocks. So basically, we want to train policies that on a set of chip blocks, and once they're trained, we want to use them to quickly generate a high-quality placement on unseen chip blocks. To this end, we started with just doing the most basic thing, and that was to train a policy on a family of chips and then use it right away on a new test chip. And that didn't really work well. We tried other tricks like freezing different layers of the policy and fine-tuning it on the new chip block, and that didn't work either. What ended up working in this case was to take a supervised approach to the way we designed the encoder architecture for this policy. What we observed was that the value net that we had for the policy was not able to generalize to new chips in a way that it was not able to predict the quality of placement, such as wire length, congestion, and such, or the unseen chip blocks. So we tried to focus on this problem of supervised prediction of the reward function first. What we did was develop a training data set with 10,000 different placements across 5 chip blocks. And these placements had varying degrees of quality in terms of like wire length, in terms of congestions. Some were better and some were worse. And then we developed a new architecture heavily focused on the representation of these chip netlists. So basically on the input side, we would get a representation of the canvas and the placement so far, the new macro that is going to be placed, and also a representation of the netlist and all the edges and the connections between the nodes themselves. And on the output side, we were going to predict congestion and wire length metrics. We tried existing graph neural net architectures, and they didn't work really well for us. And what we ended up doing was developing a new method which heavily focused on edge representations. So we explicitly assigned weights to be learned for edge embeddings. So we simultaneously updated the node and edge representations. Eventually, this graph representation was able to predict wire length and congestion well. And in this slide, you can see how these predictions work. Basically, once we had this representation that was really well at predicting the reward function, what we did was taking that architecture, placing it on the encoder side of the policy, and then on the decoder side, we used a multi-layer of deconvolutions in order to kind of predict the actions. In this case, was where to place a new macro. We also used a mask, which was very important for the policy to train. And what the mask function did was basically to allow the policy to only choose actions or placements that were feasible at that point. For example, if a macro is going to have overlap with an existing macro, that action is no longer feasible. So with this mask function, we could really enforce that. In this animation slide, we are basically showing how this generalization works. On the right side, we have a policy that is pre-trained on a set of netlists, and we applied it directly to a new netlist, in this case, a RISC-V Ariane block. On the left side, we are training this policy from scratch for the same block. And what you can see here is that the policy trained from scratch, it takes a while for this policy to come up with optimized placements, whereas on the right side, right in the beginning, the pre-trained policy knows to assign a space in the middle for the standard cells and place the macros, and those are the small squares you see on this slide, on the peripherals of the canvas. So what's happening here is that the pre-trained policy actually learned how to deal with this new netlist really well, really quickly. So here is a slide showing how this pre-trained policy helps us achieving better results and also achieving those faster. In this case, for example, we are getting optimized placement more than 30 hours faster than the policy that is trained from scratch. Here is another slide that kind of encourages us to extend the pre-training on more and more netlists. The policy that is trained on 20 blocks in this case can achieve optimized results much quicker than the other two policies that are trained on a smaller set of blocks. And this is really a unique property that deep learning and representation learning in this case is helping us observe, because none of the existing methods to placement can really become better as they solve more instances of the problem. And the good thing is the number of chips that we are placing is only going to increase over time. In this slide, we're comparing our method to prior academic state-of-the-art method and the true prior state-of-the-art, which was the manual baseline, a team of physical design experts generating these placements on Tpu blocks. What we see here is that we compare favorably to the manual design, and we can do so in under 6 hours using automated methods, whereas the baseline takes several weeks and requires human experts in the loop. So to summarize, we developed a new deep reinforcement learning method for the task of chip floor planning. Our method converges in under 6 hours. It was already productionized. We recently published this work in Nature, and this work generated a lot of interest, and we think this is just the beginning, and the whole process of chip design can really be transformed with deep learning. Thank you.
I'm a student at the University of Manchester, and I've developed Yoga AI. I've basically classified 6 main poses. So as you can see, if you hold the mountain pose for 10 seconds, the counter starts going down, and if it notices you're not doing the pose, it stops. And then once it detects another pose, and if it's wrong, the timer restarts.
I use Three.js, which is a JavaScript library, which allows you to visualize a 3D object, attract the face of the user with a pre-trained face tracking model in Tensorflow Js. It moves as I move, so it works left or right or up and down.
That really pops out of the screen. That's amazing. It's so realistic.
What we created was a sports platform that helped teams, amateur teams, such as myself, to access sports performance data and statistically easily and affordably. So we created a platform that enables both coaches and players to use artificial intelligence and TensorFlow models to generate the performance statistics they need to understand why are they winning games or not winning games, and how can they improve their performance, whether it's from a conditioning or from a skills perspective. And that is, in a nutshell, is team sports.
What you're seeing is a very short looping video clip of a martial artist doing his routine. And what I'm doing is using Movenet to extract the pose of the different body parts and extruding it in both time and space in augmented reality, so that you get this 3D form/visualization.
This project was made as a sort of demonstrator project to show how can we make autoencoders, how can we use them in TensorFlow Js. We're sampling not digits, the MNIST data, but a different data set, the Celeb A data set, which is a really great data set of celebrity faces.
We try to see how could we make a website that you could just interact with just your hands. So you need to do like a drag gesture to move things around, and you need to do like hover your hand over an object to kind of select it, and then spread your fingers to click it.
So TensorFlow JS, I realized that all the building blocks were in place now, and I could actually build an end-to-end system that would solve Sudoku puzzles in your browser. And you can see it's scanning the puzzle and solving it as we scan over the images in the newspaper.
So a couple of months ago, we open sourced this project called Pose Animator that allow you to use your body to animate your SVG characters. SVG, as it is, still requires quite a bit of design expertise to create, but we want to lower the bar even further so that anyone can create a character and animate them.
Recently, I've been exploring using TensorFlow JS with Imagery. If you think about looking at a map and you see it's almost like a photo draped across the world. So that's satellite imagery. So we've been looking at using satellite as well as drone and UAV imagery to recognize objects. And fundamentally, if we look at the TensorFlow JS sample website, we've got the webcam sample where you can show an object and it can show back what that is. You can do the same techniques with imagery in GIS.
Okay. As you can probably tell, I'm a huge fan of VTubers, which is why I'm currently in this form. I've been working on a lot of VTuber web apps that allow you to do real-time motion capture directly in the browser.
I was thinking, okay, and could we do this in JavaScript using TensorFlow JS? And
here it is.
Here it is. It works. Yeah. In the terminal, we start the driving script, which uses the model we have built to drive a car. And you can see it drives. It knows only two commands. The positive value is turn right and the negative value is turn left. And the car drives pretty well.
Hi everyone, I'm Joana Carrasqueira and I'm a Developer Relations Program Manager at the TensorFlow team at Google. We've been having an amazing event and I'm very excited to be here with you all today and talk about how you can get involved in the TensorFlow community. For the community team, providing a good contributor experience is at the core of what we do. We focus on creating systems, resources, and documentation to empower you as a contributor and help you scale your work. We welcome all contributors, either they are beginners, intermediate, or advanced professionals. And regardless of where you are in your machine learning journey, we have a path for you. I'm going to highlight some of the ways through which you can join the community, depending on your proficiency with TensorFlow and desired areas of contributions. If you are getting started with machine learning, looking for a mentor, or simply trying to make your first contribution, then I invite you to create an account and join the TensorFlow Forum. The Tensorflow Forum launched in May at Google I/O, and it's the first central platform that allows community members to connect with project leads and the Tensorflow team. This is the right place to socialize ideas and learn the latest about TensorFlow. More than 2,500 developers from all over the world have joined the TensorFlow Forum, so join us today and follow the Getting Started tag in order to find relevant discussions and tips from those who are also getting started with you. This is what the forum looks like. We created a forum experience that enables you to follow the tags and categories that you might find interesting. As I mentioned, if you are getting started, you may want to follow the Getting Started and Community tags. Here you will find not only the latest about our community, but also tips and recommendations of where to start, as highlighted in this slide. There are very exciting conversations happening on the forum, and I strongly encourage you to be a part of it. If you're looking to contribute code to TensorFlow, the RFC process is a good way to get involved. The RFCs, or requests for comments, are a great way to get feedback on large open source projects. Therefore, this is the primary way we communicate our design rationale and receive feedback. This way we give core and non-core contributors a chance to propose an idea to everyone before implementing a change. If you want to propose a design, we strongly encourage you to socialize your idea, recruit a sponsor, write your RFC, respond to feedback, and implement it. Our contributor ecosystem welcomes many different types of contributions, including code, non-code, and documentation. For bigger projects in which we have to work as a team, we created the TensorFlow Special Interest Groups, which are groups with a defined project focus. This is a program that organizes contributors into focused streams of work, and these groups take ownership of specific areas to add and maintain new features. Currently, we have 14.6, and I would like to highlight the latest addition to the 6 program, the TensorFlow Recommenders Add-ons project, which makes large-scale recommendation easier and widely adopted in the community. If you are interested in contributing to any SIGs based on the parts of TensorFlow that you enjoy or care about the most, head to GitHub for more information on how to join. You can also request a new SIG, and we are here to guide you through the process. Another program that I would like to talk about is the Google Developer Expert Program, which welcomes developers from all over the world. Our machine learning GDs, they play a critical role in advancing machine learning education worldwide, and they act as technology ambassadors. Just this year so far, our machine learning GDs reached more than 1 million developers throughout tech talks, workshops, blogs, and videos. If you would like to learn more about the GD program, head to developers.google/community/experts, or feel free to reach out to any of the GDs on the TensorFlow Forum to find out more about their personal experience with the program. Be an authority in the community and increase your proficiency in machine learning by taking the TensorFlow certificate. Employers use this network to find talent, so showcase your skills and maybe land your next ML job. We also have stipends available, and for more information about the TensorFlow certificate, please visit tensorflow.org/certificate. We have many educational resources available to help you build and train powerful models. Learn how to design an ML production system end-to-end with our course on MLOps on deeplearning.ai. We also offer more courses on topics such as TensorFlow Advanced Techniques and Data and Deployment Specialization. Lastly, I would like to highlight our TinyML Harvard Professional Certificate, where you can learn how to program in TensorFlow Lite for microcontrollers. Follow these links to find out more about your desired course. And last but not the least, for a chance to be featured on the TensorFlow social media channels, please submit a cool project or demo that you created using TensorFlow. I'm always excited to see what the community creates every month, and this is a great opportunity for you to get recognition and increase your profile in the community. We feature our community spotlight winners on Twitter and the TensorFlow blog. Thank you all for your commitment to our community. We couldn't have done it without you. Finally, I strongly encourage you to get involved in the TensorFlow community. Join the MLGD program or the 6 program. Get certified with the TensorFlow Certificate program or take any of our courses to advance your machine learning proficiency. Don't forget to submit your cool project or demo to be featured on the Community Spotlight program, and if your city or country doesn't have a TensorFlow user group yet, then you have the opportunity to start the first group. Let's stay in touch on social media. We have a YouTube channel with fantastic free educational content, a Twitter account where we share the latest news about TensorFlow and recognize the fantastic work of our community members. And lastly, check out the TensorFlow blog for technical content, stories, and use cases on how to use TensorFlow. And of course, for a more personal touch and to stay connected with the team, I'll see you on the TensorFlow Forum. Thank you.
When I was 22 in 2012, I was involved in an electrical accident at work, which resulted in an amputation of my right hand. Music and drums was my passion. When I lost my arm, I was very negative about things, just thinking about what I couldn't do. But after the first month, I was like, you know what, I'm just gonna pull my drum kit out of storage, tape the drumstick to my arm, and proceeded to play it. That was a turning point for me. It was letting me know that it was possible. My current prosthetic is what you call a body-powered prosthetic. It just uses basic mechanics. I use a lot of my shoulder and elbow to kind of exaggerate to get the hits that I want. It also has limitations on how fast I can play.
Like, that feels like it might be a little too slow.
Yeah, it's a weird one. So I had an idea of developing a robotic drumming prosthetic, and I knew Gil Weinberg was the right person to reach out to.
I understood immediately what he wanted. He wanted to sense more of his muscles and be able to control the bounce of the drumstick. I was a little worried. Can we provide him with what he wanted in terms of the latency and the control? We didn't know that it's possible. Now, it's not a big problem when you want to grab a cup, so you wait a few milliseconds. But when you play music, you need to immediately hear the sounds that you play. And that's where we looked at all kinds of different motors, and TensorFlow was perfect for this project.
So we basically use TensorFlow as a tool for the deep learning trainings based on the data we collected through the EMG sensors.
We need to see what kind of electrical activity happens when he's moving his arm in different ways.
And then through the TensorFlow Lite, which is actually a more efficient tool to use, we can apply that to the Raspberry Pi, a small device that is implemented as a general console. And the TensorFlow model will actually predict Jason's gesture based on how he moves his muscles.
TensorFlow Lite provided us with exactly what we needed, much more streamlined, faster. It also reduces the latency.
The latency, it's like none.
That's awesome. Usually in university labs, you make prototypes that can just symbol what can be done. And I think, finger crossed, that this arm is going to last for years, just like a product.
I can actually feel the feedback from the arm, and it feels as close to a real hand as you can get without it actually being a real hand. The possibilities of this kind of technology with TensorFlow and everything combined, you could make almost anything you can think of.